Hi children, welcome to math class. Dear children, in this class we are going to learn about the factor theorem, and we are going to solve some problems which are based on the factor theorem. Okay, let's have a look on the factor theorem first. If px is a polynomial of degree n greater than or equal to 1 and a is any real number, then x minus a is a factor of px if pa equal to 0. And the second statement, if x minus a is a factor of a polynomial px, then pa equal to 0. Children, if you have a polynomial that is named as px of degree greater than or equal to 1, and this polynomial is divided by the linear polynomial, and you got the remainder as 0, and then you can say that x minus a is a factor of px. Okay, and the second statement, this statement is converse of the first statement. Here, if remainder is 0, then you say that x minus a is a factor of px. And the second statement is opposite. If x minus a is factor of a polynomial px, then pa equal to 0. In the first statement, remainder when px is divided by the x minus a is 0, then x minus a is a factor of px. And in the second statement, this is converse of the first statement. If x minus a is a factor of a polynomial px, then remainder is 0. Okay, let's prove the theorem. Proof. Let px is any polynomial which is divided by a linear polynomial x minus a. The quotient be qx and remainder be rx. Children, here we are assuming that a polynomial px is divided by the linear polynomial x minus a. It gives the quotient qx and it gives the remainder rx. Okay, I wrote the statement that represent this figure. Okay, so by using a division algorithm, we can represent this data as by division algorithm. Dividend equal to, that is px equal to divisor into, that is x minus a, into quotient, that is qx, plus remainder rx. Okay, children, you know that by using remainder theorem we can get the remainder without doing the actual division. That is, if you substitute 0 value of the linear polynomial x minus a in px, you got the remainder. Okay, by remainder theorem, here I am changing rx value. So by remainder theorem, remainder is if you substitute 0 value of the polynomial x minus a, that gives the remainder. That is, we have to substitute a in the place of x. Okay, that is by remainder theorem, px equal to x minus a into qx plus remainder, that means pa. Okay, so first condition, we have to prove the first condition, that is x minus a is factor of px if pa equal to 0. In case remainder is 0, then you can say that x minus is a factor of px. Okay, so that is the first condition, the first one. If pa equal to 0, then So first condition is if remainder is 0, then x minus is factor of p of x. So that's why I'm taking remainder is 0, that is pa equal to 0. Now substitute this value in the above equation, then px equal to x minus a into qx plus 0, because here pa equal to 0, that's why I'm substituting pa as 0. So therefore you can get px equal to x minus a into qx. Okay, so its value, that is px, he here we can write px as a product of two numbers, that is x minus a into qx. So you can say that here x minus is a factor of px and qx is also a factor of qx. Okay, so our statement, we need to prove x minus is factor of px. Okay, don't get confused children. 6 means 2 into 3, we can write as 2 into 3. That means here 2 into 3 is a factorization. That means you can write 6 as a product of 2 or more numbers. Here 2 into 3 means we can write 6 as the product of two numbers. In these two numbers, 2 is a factor of 6, also 3 is a factor of 6. Okay, so if you write any value in the product of two or more numbers, each value which are involved in the factorization is a factor of the given number. Okay, so another example, if you write 6 as a product of 1 into 2 into 3, 1 is a factor of 6, 2 is a factor of 6, 3 is a factor of 6. Okay, so in this case also we can write px as the product of x minus a and qx. That's why x minus is a factor of px and qx is also a factor of px. So but here we need only x minus is a factor of px. That's why you can say that here x minus a is a factor of px. Okay, hence case 1 proved. Okay, now the second case, that is second one means if x minus is a factor of px, then pa equal to 0. Okay, so condition given here is x minus is a factor. Okay, since x minus a is a factor of px, x minus a is a factor of px, then you can write px equal to x minus a into qx, where qx is some polynomial. Okay, children, x minus is a factor of px, so you have to write px as x minus a into something. So here something is qx. Okay, that means you can write px equal to x minus a into qx. Okay, now substitute a value in this polynomial. Let us check what will be the result. If I substitute a in the px, that is it will be a minus a into q into a. A minus a means 0, 0 into qa, 0 into something 0. So pa equal to 0, that is remainder is 0. Okay, so that is the second case. If x minus is a factor of a polynomial px, then pa equal to 0. You have to prove that by taking the condition x minus is a factor of polynomial, and you have to prove pa equal to 0. That is we have proved here. Since x minus is a factor of px, that's why you can write px as product of x minus a into some polynomial. Here I am taking some polynomial as qx. Now substitute a in this polynomial, you can get the result 0, that is pa equal to a minus a into qa. A minus a equal to 0, 0 into something 0. Okay, hence case 2 also proved. and case 2 also proved. Okay, this is the remainder theorem. Okay children, it's very simple. Remainder theorem means if you divide any polynomial by the linear polynomial x minus a, and if you got the remainder 0, then you can say that the linear polynomial which divides px is a factor of the polynomial px. Okay, and this and the converse of the statements is also true, that is, if x minus a is factor of a polynomial px, then the remainder is 0. Okay, simply you can understand this. Here px is 6. Our common experience tells us factor concept. Here 6 is a number that is dividend, and it is divided by the value 2. 2 3s are 6, the remainder is 0. Okay, since remainder is 0, so you can say that 2 is a factor of 6. Here also, if any polynomial px is divided by the linear polynomial x minus a and it gives the remainder as 0, you can say that x minus a is a factor of px. Okay, and the converse of the second statement, x minus a is a factor of a polynomial px, then pa equal to 0. Here you can observe this converse of the statement also. Since here remainder is 0, 2 and 3 are the factors of 6. In this way, if x minus a is a factor of px, that is remainder is 0. So this you can observe the, you can notice the converse also, that is, if remainder is 0, you can say that x minus is a factor of px. Okay, don't get confused, just watch carefully, you can able to understand this factor theorem. Okay.